started. So good afternoon, ladies and gentlemen, to another Risk Institute online session, and a happy new year to you all. Today we're fortunate to have with us Dr. Georg Schollmeyer from LMU, who's going to be talking to us today about partial identification in regression analysis. But firstly, let's just make a few announcements. So the following talks that we have lined up are for the 18th of January. Sorry, I've repeated the same thing here. But incorporating food and the gut microbiota in the 21st century risk analysis by Miss Peg Coleman on the 18th of January at 3 p.m. Then we have Professor Ekaterina Aua, which is the following week. I believe that's meant to be the 24th or the 25th of January, talking to us about assessing the likelihood of mutations in BRCA 1 and 2 genes with interval and Dempster-Schaeffer theory-based methods. And then on the 1st of February, we'll be having our Risk Institute annual showcase where we'll be having a kind of range of our PhD students and some alumni presenting to us their current research. And then our next talk after that to be announced is from Dominic Hose on the 5th of February. So without further ado, I'll introduce our speaker. So Dr. Georg Schollmeyer is a postdoctoral researcher in the working group Foundations of Statistics and Their Applications, headed by the Thomas Augustin at the Department of Statistics in Ludwig Maximilians Universität in Munich. After studying mathematics at the Technische Universität in Dresden, he went to Munich to make a PhD in the field of imprecise probabilities, which is obviously of a lot of interest to us. And under the supervision of Thomas Augustin, he worked mostly on imprecise probabilities and partial identification statistics. So now he's doing his habilitation at LMU, again under the supervision of Thomas Augustin. So thank you very much for joining us today. And if you'd like to start sharing your slides, Dr. Schollmeyer.
Then thank you very much for the introduction. Also from my side, Happy New Year to all of you. I'm very happy to give a talk about research of our working group about partial identification, especially in regression analysis, because we are working mainly in the field of statistics. And I want to speak about, say, two contributions. One is a little bit older, from 2013, and the other is a little bit an earlier paper or a newer paper from 2021. And before we start, I would like to introduce to you in a very informal sense the problem of partial identification. And we are starting with classical linear regression. And please think of, to make it simple, about a simple linear regression. So we have an outcome variable y, which is in a linear relationship with a covariate x, and we have an error term epsilon. As you can see, this slide is titled part 1. So we have two parts. And the first part is about old research, which we did about the case where the outcome variable cannot be observed directly. And in part 2, I will speak about other research which is focused on the situation where also the covariates are only partially observed. If you have any questions, please feel free to interrupt me. Okay, so this is something like an overview for the first part. We have a linear regression model, and we cannot observe this y. We only observe bounds for this y. And because we are concerned with linear regression, we can try to estimate these parameter vector beta. And depending on which concrete model understanding you impose on this regression relationship, you obtain different so-called identification regions. And what this is I will explain now. So the basic situation is the following. We have, for simplicity, a simple linear regression model. So y equals x beta plus epsilon. So this big X is here a matrix, the design matrix. Or if you write it completely, then you would say, okay, y is intercept b0 plus a slope beta 1 times one covariate x1 plus an error term. In the sequel, we will focus on the slope parameter. So think only about the slope parameter mainly. And in the classical case, you can estimate these beta consistently, for example, with the method of least squares. And now we have the situation that this y, the outcome variable, is not observed, and we only observe bounds, y lower and y upper, and we only know from these bounds that they contain the true outcome variable y. I would like to make an example. One typical example is, for example, in social surveys, where you ask, for example, the respondents about their income, then often the respondents will not answer the question about the income. And one way to reduce the non-respondents rate is, for example, to ask not directly the income, but to ask the income in categories. And there are still further subtle sampling designs where you first ask, is your income within the interval from 1,000 to 2,000 euros? And if the respondent asks this question, then another question is asked, is it between 1,500 and 1,600 euros, and so on. And therefore, for every respondent, you have an interval valued observation, but you do not know how the true unobserved y is distributed within this interval. So you cannot somehow make an assumption about this distribution. This is a problem, and which leads to the case that we cannot consistently estimate the slope parameter, for example, in general. The reason is that there are different slope parameters with different censoring or coarsening processes, which lead to the same distribution of all observable random variables. So we observe the x, the y lower, and the y upper, but different settings of the coarsening process and the error term and the slope parameters would lead to exactly the same distribution of the random variables we can observe. And therefore, of course, one cannot consistently estimate the true parameter, because this true parameter is generally empirically not distinguishable from other parameters which lead to the same distribution of all which we can observe. This is the basic situation, and of course, our object of interest is in fact the true parameter. And we know now, okay, in this situation, if we do not want to impose further modeling assumptions, we know that the true parameter is not consistently estimatable. And what will be the solution? The solution in partial identification is that we do not try to estimate the true parameter, but we try to estimate some set for which we know that this set contains the true parameter. And so one could say that the set of all parameter vectors which are compatible with both the imposed model assumptions and the distribution of all random variables which we could observe, this set of all parameters is called the identified set or identification region. And we try to estimate this identification region. One point I want to stress here is that there are two sources of uncertainty here. The one is that the parameters are not identified, and the other uncertainty is, of course, the statistical uncertainty, because we can observe our y lower and y upper, and with this we can estimate their distribution, but we can of course not estimate it without some error. So we have the statistical uncertainty, which leads to the fact that we have only an estimate of the distributions of the observable random variables. And then we have given this uncertainty, the additional uncertainty that the true parameter vector is not identified. This especially implies that also with an infinite amount of data, we have still an unidentified situation. So also with an infinite amount of data, we can, of course, estimate the distribution of all observable random variables arbitrarily precisely, but we cannot solve the problem that the parameter, the true parameter, is not identified. So there is still some uncertainty, some non-stochastic uncertainty remaining. And so we will then end up with a set, the identified set, and then we have additionally to estimate this identification set. And about the estimation, I will speak later on. First, I would like to speak about the identified set. So for this, we can, in the first step, think as if we would have an infinite amount of data, and we only want to define identification regions. The identification region is, like it's written here, the set of all parameters which are compatible with the model assumptions. And of course, depending on the exact assumptions which you impose, you come to different identification regions. And here I like to make a prototypic differentiation between what David Friedman has called structural models and descriptive models. I will explain it shortly. A structural model is something which is obtained if you really take your model assumptions very seriously. For the linear model, especially, we would then assume that really the y is in a linear relationship to the x, or more correctly put, the conditional expectation of y given x is really a linear function in x. And then the problem is to find the intercept and the slope of this linear relationship. This would lead then to one identification region, and I will illustrate it in a few seconds. The other model understanding is a more descriptive model understanding. In this setting, we do not assume that the relationship between the conditional expectation of y given x and the covariate x is linear. We do not assume anything. We only say that, okay, given some x and some y, we are simply interested in the best linear predictor under squared loss. So concretely, we want to find or estimate a prediction function f, which is linear in x, and which minimizes the expected loss of the observed y compared to the prediction that is made by f. I will explain this later in detail. And based on these two assumptions or two model understandings, we come to two different regions. Here we call that the first region mirror region and the second collection region. And finally, I would like to additionally present another identification region, which is not so much in the spirit of partial identification, but we will see this later on. So now I will start with the mirror region, and the idea here is really simple. So first, or in the first step, let's assume that we have an infinite amount of data. Then we can, for example, compute or estimate conditional expectations arbitrarily exactly. So, and then here I try to illustrate a situation where I have on the x-axis the covariate x, and on the y-axis the conditional expectation of y given x. Because y is not observed, we do not know the conditional expectation of y given x. but we observe the bounds y lower and y upper, and therefore we can compute the conditional expectations of y lower and y upper given x, and this is illustrated here with this upper line here for the expectations, the conditional expectation for y upper, and here the conditional expectation of y lower given x. And the idea is simply that, okay, now we want to define this narrow region as simply the set of all regression parameters such that they completely fit to the model assumptions and the data. And this could be defined in the following formula here. Take every linear function described with intercept and slope defined by beta, such that the conditional expectation given for this linear model is in accordance with the things which we observe. So it's below the conditional expectation of y lower, above the conditional expectation of y lower and below the conditional expectation of y upper. Or to make it graphically, simply take every line which fits through these the boundaries y lower and y upper. So I illustrated this here. So some lines which are completely within this band. And if I take all such functions, I have the set of all such functions. And this would be the definition of my identification region. Okay, this is, of course, relatively simple. But of course, this is only the view that we have an infinite amount of data, and we can estimate these conditional expectations arbitrarily precisely, but this is of course not realistically. Another problem is that if the true underlying relationship is not linear, so if I have a misspecified model, then this set here, which is defined here, can also be empty, because there is maybe no line which completely lies in these boundaries. This is one problem. Because I want to speak later a little bit about the estimation, I will also add a further representation of this narrow region as the argmin of some criterion function. This looks a little bit very complicated, but it's not very complicated. This function q is a function which has as arguments beta 0 and beta 1. So a line is the argument. And if this line completely fits to the boundaries here, then this value of q is 0. Otherwise, it's positive. For example, if I have a line which goes in this way, that here it is somewhere above the upper boundary, then the area between this line and this upper boundary is integrated here, and then we get a positive value. So somehow this q function measures the property of a function of being within this boundary. So if it's 0, then it's completely in these boundaries. If it's positive, then it's somewhere below or above the boundaries, and it's very high, then it's very much away from these boundaries. And with this, one could then say, okay, the narrow region in its original definition would be the set of all parameters where this q function is 0. And for a misspecified situation, we can say, okay, then take, for example, every parameter vector such that this q value is very small. So the argmin, for example, or below some threshold. Okay. Now I will come to the collection region. This is maybe still more simple. For this collection region, we do not assume anything about the relationship. So we take every arbitrary random variable called z here, which is compatible with the observed intervals, y lower and y upper. but the set needs not to be linear in X. So I've illustrated this here with this gray line. And for every such set, we simply compute the best linear predictor. So the prediction function y hat, it's called here, such that the expected quadratic difference between y hat and z is minimal. So for every possible set, I compute the best linear predictor. For this gray function, for example, I will get this line. And you can also see here that this line is below the lower bound. If you compare this to this collection region, then due to the construction, of course, this whole region is then completely within the boundaries. And for this approach, it's not the case anymore. And if I compute all such functions, then I will get this purple set. And you can already see that the obtained region is a larger region than the narrow region. Okay, so now we have two regions, and the difference is really due to the appropriate handling or inappropriate handling of the linearity assumption. If I really assume that the relationship is truly linear, then I will come to the narrow region. Otherwise, I will come, for example, to this collection region. So now I want to additionally define a third identification region. This identification region is not so much in the spirit of partial identification, but maybe it's a little bit in the spirit of imprecise probabilities generally. And the idea here is, in the first place, very simple. So we already know in the partially identified situation, we cannot consistently estimate the true parameter. We have somehow to find sets of parameters. And the idea is now that we directly do not look at the parameter space itself, but we look at the space of all sets of parameter vectors. And for every such set, we try to invent something. So these sets here are called always big gamma. And the idea is that we would like to find the set gamma for which the predictions made by this set and the things we observe are fitting good together. And the idea is the following. For such a set big gamma, we compute first the upper expectation and the lower expectation as these point beta ranges in the set gamma. So for every x, we simply compute the highest prediction, which would be made by some beta in the set big gamma, and additionally the lower prediction. So with every set, I have an upper prediction function and a lower prediction function. And then I try to find that set big gamma for which these upper predictions and the upper bounds which were observed, as well as the lower predictions and the lower observed values are close to each other. The formula looks a little bit strange. I will not go too much in the details. This could be done maybe in the discussion afterwards, but I will only make it graphically. So in gray, I depicted here for some arbitrary set gamma, the associated upper and lower predictions. And then I simply measure the deviation between these predictions and the boundaries with some integral form. So to illustrate this, this is somehow the area which is depicted here in gray. And then I will try to find that set big gamma for which really this area is very small. And concretely, I would come to this prediction. And this prediction is made is made by the set of all functions which fit between these green boundaries. And with this, I have another identification region. So a very important difference compared to the other identification regions is that in the first step, we went from the parameter space to the space of sets of parameter spaces. So we do not know how to interpret this in the first place with respect to the original parameter space. Note that we are actually really interested in the true parameter, not in sets of parameters. About this, I would like to speak in a few seconds. I will only want to show how then these identification regions look like. On the left side, you can see in black the upper and lower conditional expectations, and then the predictions made by these three identification regions. I think it's a little better to see in the right picture. There you have depicted the parameter space of the associated regions. And then you see in purple, this is this narrow region. Here you can already see it's very large. Then in red, the smallest set here is this narrow region. Also, that's the name narrow region. And in green, this settlers region. Okay, this was first only the definition, and now I would like to say something about the properties of these regions. And please note that also we did not speak about estimation of these regions at all. This will come in a few seconds. So first, for the narrow region, the narrow region assumes that the true relationship is really linear, and therefore if the model is misspecified, one cannot usefully interpret this region. So it's somehow meaningless in the misspecified situation. Furthermore, if you analyze this narrow region as a mapping, where you map the observed boundaries to the obtained region, then this mapping is not continuous. So it's somehow an ill-posed problem, and therefore it's mathematically and also from a statistical point of view very unnice to work with such a mapping. Then I will come to the collection region. The collection region collects every best linear predictor, and the best linear predictor does not depend on the fact that the model is correctly specified. So the collection region would also be meaningful in the misspecified situation. But one disadvantage seems to be that this region is often very uninformative. Maybe I will go back to this picture here. For example, here for the lower prediction made by this collection region, this is this purple prediction. This is always below the original conditional expectation here, with which I start. So somehow it looks a little bit like with this region, I cannot get much information about the true underlying relationship. Then for the settlers region, one can show, and this is the only reason why it's useful to work with the settlers region, that if the model is well specified, then also the settlers region contains the true parameter. And therefore we could, with this, go back from the space of sets of parameters to the actually true parameter which we are interested in. Also in the misspecified situation, we can interpret somehow this region, because we can say, okay, this is that region for which the predictions, the upper and the lower predictions, are closest to the observed boundaries. Then one a little bit strange property is that the settlers region is not isotone. With this, I mean simply if you have a situation where you have intervals y low and y upper, and then you make the intervals sharper, then it can happen that the corresponding region will not get smaller, but would be something else. So this is a little bit very unintuitive, but yeah, this is as it is. Okay, so all regions have some strangeness, I would say. And now I will only say something about estimation. And in the literature, the most often thing which is done is simply that you replace all unknown things, for example, these conditional expectations, simply with the conditional means based on the observed sample. And then one can do asymptotic analysis and so on. And for the case of the collection region, there's a big literature which uses random set theory. And this works somehow fine. One has also asymptotic normality results. And one works with random set theory and uses the concept of distances between sets of parameters. And this works fine. And for the narrow region, one works with this criterion function. And what one does is that one simply take an empirical analog of this criterion function Q and collects every parameter vector beta such that this empirical criterion function is below some threshold C. And then one can show if C goes to 0 as n goes to infinity, then under certain other conditions, this would lead to a consistent estimate of this region. However, this concrete assumption is something like that the C alpha goes with order 1 over square root n to 0, but it's not said that should I take 1 over square root n or 2 over square root n or 10 over square root n. So there is no real guidance for how to exactly choose this constant C here. And this is maybe somehow a general problem. We cannot really calibrate the size of these set-valued estimators, because so here if I have C which is larger, then the set would be larger, and how to exactly specify the C alpha is, I would say, something like an open problem. Okay, then I will only say something about computation, but I will only speak shortly about this collection region, because for this collection region you have to compute the best linear predictor for every possible y which is or set here which is compatible with what we observe. And this analysis very easily, you can use linear algebra, and this is well studied in computational geometry. And the reason why it's simple enough is the fact that these x, which are here, are precisely observed. So you can simply compute this matrix here, and you only have to care about these sets, which are ranging, but only in these boundaries y lower to y upper. So this is simple. And with this, I would like to come to the last part 2, which is also a little bit shorter. In this situation, it's still more difficult. In this situation, we look at the case where not only this y is not observed, but also the x is not observed, and we only observe boundaries for the covariate values x. So we know, okay, x1 is between 10 and 12, for example. And then you can think the whole thing again. And I will only like to speak about the two aspects here. One which treats the model more like a structural model, in the sense that the linearity assumption is really assumed. And the other thing I would like to start with is the completely descriptive view. So I will start. And the first idea one could have is that you say, okay, I can try to make the same things like for the collection region, and then I have to compute the best linear predictor, which is written here. but now I have to care about the fact that this set ranges in intervals and also the covariates ranges in intervals, and then I have to analyze this set. And the problem is that this is really computational very demanding, and there are some possibilities for doing interval arithmetics. This is not the point I want to speak about here. I only want to speak about another idea. I called it rethink the problem. So for this collection region, the idea is simply to reduce the problem of the estimation to first look at every possible random variable or data sample which is compatible with what we observe, and then to compute the best linear predictor. And so in this idea, we do not think directly about the best linear predictor. We only think about how to usefully estimate the slope parameter. And the idea is based on the following simple observation. If I have two different data points and assume that they are precisely observed, then we could identify this beta, so the slope and the intercept. And now we only want to look at the intercept. And I have made here a picture. So you have some 1, 2, 3, 4, 5, 6, 7 interval value data points. And I will look on this data point A here and this data point B here, which is in the form of an interval. And if I knew where the data point exactly, the unobserved data point exactly lies, I have illustrated this here with this blue point and this blue point, then I could simply draw the line through these 2 points. And then I can compute the slope. And one can easily see that with this slope, we have an unbiased estimator for the true regression slope. The problem is now, of course, that we do not know where these blue dots are exactly lying. But of course, we can simply take the most extreme cases. For example, the green line would be the line which would lead to the largest slope. Actually, I see now that the picture is a little bit wrong. This should be the line from here to here, because then the slope is larger. This is a mistake. The line from here to this point here would be such that the slope is maximal, and the red line is the line which would lead to the smallest slope. And with this, I can try to invent some estimator and in the following way. So we do not have only 2 data points, but n data points, and then we can simply look at every possible pair of 2 points, and then for every such pair, I can compute the slope, or more precisely, the maximal or minimal slope, which can be obtained as the precise values, the possible precise values range within the intervals. So these green and red lines. For every such pair, I have a green and a red line, and then I can try to aggregate all these lines in a certain sense. So first I want to say, okay, every such estimator based on 2 data points is an unbiased estimator of not the true parameter, but an unbiased estimator of some upper bound of beta 1, and the same for beta 1 lower. And then I can aggregate this to get a further unbiased estimator of some upper bound for beta 1. And because I take more than 2 data points or 2 pairs of data points, I can hope for the case that the variance of this estimator is smaller compared to if I would only take only 2 data points. And you can simply then, with every such estimator, aggregate them with, for example, the weighted mean. You can also take a weighted median or something like this to make it more robust and so on. There are many possibilities. But then with this, you can get an estimator of an upper bound. And if you do it in the right way, if you weight the estimators in the right way, then you can make it in such a way that the variance of this estimator is minimal. So one can, because it's not too complex here, these estimator, we can really analyze systematically the variance of this estimator. If one takes different forms of weightings, and then one can systematically choose the range in such a way that the variance is minimal. So with this, we have, in a certain sense, an estimator with minimal variance. And one can then still analyze further the situation. And for the extreme case where both x and y are not intervals but precisely observed, then this whole procedure would lead to an estimator which coincides with the classical least squares estimator, which is, of course, a nice property. And additionally, if we would know the variance of the error term, then we could also do inference, confidence intervals, and so on. Of course, the variance of the error term is usually really not known. So we have here a problem, but there are some formulas which give you at least upper bounds for the error variance. And you can use these estimators or these upper bounds to make at least a conservative confidence intervals. And therefore you have at least some rough insight about the statistical uncertainty. Okay, this was about the second situation. And now I would like to conclude. So we have defined different identification regions for linear regression analysis. And we discussed some properties of these regions and shortly touched the problem of estimation from data, which was simply replacing all unknown terms with sample analogs. And what's interesting for me, at least, is the role of this model understanding. So if I really assume a linear relationship, then I come to other conclusions compared to if I do not assume this. Yeah, and then maybe a last point about the second part and our approach here. Somehow we use two pairs to identify the true slope parameter, but somehow for this we have to assume that the relationship is really linear. I'm at the point not so much aware how to interpret our approach in the case where we have a misspecified linear model. So this is somehow unclear. Of course, one can always interpret this as cases some certain weighted sum of slopes. So this would be the interpretation, but maybe there could be something better than this. And the last point I want to make is maybe a little bit more general, because it also applies to classical statistics without partial identification. I would say that the applied researcher should always be clear about the exact imposed model assumptions. It's not so much about disliking model assumptions, but the awareness about which assumptions are made and how much do these assumptions imply for the concrete statistical method. Okay, this was it from my side, and now we have the possibility to discuss a little bit. Thank you very much for your attention.
Thank you very much, Dr. Schollmeyer, for your presentation. It was wonderful. Can I open the floor to the audience, if anyone would like to unmute themselves and ask any questions?
I have a short clarification, so if I may go first.
Please, Adolphus.
Sure. Thank you, Francis. So thanks so much, Schollmeyer, for your talk. Very interesting. I just wanted to have a short clarification on the what's that called, the Mara region, yeah. And it's a bit because it's a new concept, all these are new concepts to me, but and I, as you explained the Mara region, I was unable to really understand, like you know, when we had the two black lines, you had the bounds, and you actually drew this faint gray polynomial line that doesn't look linear, and you're able to actually generate a linear like a linear what you call possible linear curve from that polynomial what you call estimation. So how did we actually like get from the polynomial to the linear estimates again?
So you are asking about the Mara region. Am I
Yeah,
right?
Mara region.
Okay, this is simply, I do not know if I understood it rightly, but we simply collect here in the set all linear functions which fit to the boundaries.
Oh, sorry, not the Mara region. I mean the second region. The one that you had the gray. I think collection region. Sorry, yeah, this is the one.
Yeah.
My bad. So, how do we get like you know from this from this curve, and then this is one of the possibility of the curves within this interval, right? If I'm understanding correctly.
Yeah.
And then you managed to get a linear curve from this.
Yeah. This.
How did we? Is it from this formula again?
Yeah. Okay. So this gray stuff is the set which I look at. This set.
Right.
And for this set, I can compute the best linear predictor.
Right.
Or the least squares estimator. And concretely, we would have some parameter vectors beta 0 and beta 1. And the line is simply the line which corresponds to these beta 0 and beta 1.
Oh, right. Okay.
And then in the second step, I take every such set and compute for every such set this line, and then I collect it in this set, which looks in this way.
Right, and we're going to have some realizations that fall outside the bound as a result, if that's what I'm interpreting from this figure.
I did not acoustically understood your first part of the sentence. Can you repeat?
Yeah, so like from this, is it right to conclude that there are some realizations that lie outside this interval, because there's some that is outside this where this black line actually is? Like there's some regions that fall outside the lines.
Yeah. No, I would not say that when you can conclude that some observations lie outside the boundaries, because so if I only take this situation, then I know, okay, because it's not a linear relationship, then I can compute nothing in the first place, but I can compute this best linear predictor. But the best linear predictor lies very far away from, for example, here. Especially if I go very much into the left-hand side, then the difference could be arbitrarily large. And therefore, the fact that this region is here below the lower expectation, this fact is not, how should I say this? This is not due to the fact that observations are somewhere outside here, but because we have to work with linear functions which does not fit to certain sets which are clearly not linear.
Right. Awesome. Yeah, thank you so much for your clarifications on this. So yeah, that's all I have. Thank you so much.
Thank you, Adolphus. Have we got any more questions from the audience?
Yeah, I think I do, if I can. I actually had a bunch of all little questions, I think. So first, is it the case that the Mara region will always be a subset of the set loss region, and which will always be a subset of the collection region, or is that not true?
Yeah, okay, I go to the picture and I have to think about it. So one can show that the Mara region is always a subset of the collection region. This is very simple to see, because if I take a point of the Mara region, then I take, so to say, a line which completely fits to the boundaries. And if I take exactly a linear function, exactly this linear function, then I would also, of course, with the best linear predictor, get the same regression line. And therefore, the narrow region is a subset of the collection region. And as I already did say, if the model is well specified, which means that at least one line should go to the boundaries, then one can also show that the narrow region is also a subset of the set loss region. And the relation between the set loss region and the collection region, there is no relation, so to say.
Okay.
So maybe you can think of a little bit on the special case where you have precise values. Then if you have, for example, a conditional expectation which is not perfectly linear, but for example, quadratically, then for the collection region, because it's a precise situation, we have simply the best linear predictor, which is some line. And for the set loss region, we would like to approximate the upper and the lower boundaries, which are in this case identical. And this would lead to a prediction which is not a single point, but is not described by a single parameter set. But so unfortunately, I have no example here. But if you have a quadratic form, then so if I only look at the upper bound, then I would exactly approximate the upper bound, but with this I cannot approximate the lower bound good. So this would lead to somehow a prediction which is for the upper bound approximately this quadratic function, and for the lower bound, of course, for the lower bound also a quadratic function, but in this way. So it's a little bit difficult to explain, but if you analyze it for a simple quadratic function where y lower equals y upper, then you will see then, of course, the collection region is a singleton set because it's simply one data point which you look at. And for the set loss region, you have generally a set which is not only a singleton. And for the narrow region, of course, because for a quadratic form, you know that there is no line which fits through these boundaries, then this narrow region would be the empty set for this situation.
Okay. Thanks. So when you say that that there's no consistent classical point estimator in those cases, the definition of consistency that you're using is just the regular definition in statistics, is that right? Or you have a special definition of consistency?
No, so for every definition, so for example, that the estimator converges in probability to the true parameter, already this would not work. The reason is very simple, because if I have two parameters which are indistinguishable, I cannot know which one is a true one, and then any method does not know to which point to converge, because it had.
So that means you have a special definition of consistency then, is that right?
Can you repeat, please? Sorry?
Well, that means that when you say, I forget now what it was that was defined in, I guess it's the imprecise case, that when you say that there is no consistent classical point estimator, when you say the word consistent, you're already generalizing that notion from classical terminology.
No, it's a usual notation of consistency. Maybe it's a little bit stupid from my side to say it in that way, because I wrote there do not exist consistent classical point estimators. actually there do not exist consistent point estimators at all.
Oh, okay. Okay. So yeah, I'll have to wrap my
At this
head
point, I
around
do
that.
not speak about set-valued estimator, but only classical point estimators and classical consistency in the sense of the estimator converges in probability to the true
But
power.
there are, I mean, the regular statisticians and certainly engineers in the field wouldn't mind to apply classical methods even when the data are, intervals or sets themselves. They wouldn't notice the problem. And so for them, those point estimators do exist, of course. They're just not something that would be very respectable. So it's kind of hard to talk to them when they, to say that, oh, you don't really have an answer, but they say, well, I do have an answer. Here's my answer, right? You have to talk them down from that sort of unthinking position, I guess. I have one more question.
Yeah.
You said in slide 2, when you actually on slide 1, you didn't. I don't know if you defined what CAR was. Well, what is CAR?
Oh no, sorry, I forgot to speak about this because this means coarsening at random. So this is a situation where the coarsening is in such a way that you can somehow ignore the fact that
Right. Yeah, obviously. So in slide 2, you talked about the two kinds of uncertainty, the non-identifiedness and also the statistical uncertainty. So does that suggest then that you would, and you called at one point the non-identifiedness, you call that non-stochastic uncertainty, which seems reasonable, but could you also call it then non-statistical uncertainty, or would you think that that's a bridge too far? You wouldn't want us to call it that, just as a pedagogical question.
So I would, in this case, I would use both words interchangeably. So
non-statistical and non-stochastic.
Actually, usually I would presumably say non-statistical uncertainty.
You would say that? I
would say that.
Okay, good.
So,
that seems reasonable to me because it's harder to explain, the fact that it's non-identifiable is more of a mouthful, I guess. Yeah. Okay. I guess that's. I have a lot more questions, but I think I need to read more carefully. I guess I don't really have an intuition for the Friedman distinction between structural model and descriptive model. I guess I just need to read that.
Yeah, actually, these words are not so exactly fitting to what I have in mind. But he's also speaking about causality. So that you say, okay, for a structural model, you really believe the structural relationship, and this structural relationship is due to some substance matter theory, for example.
Like an underlying mechanics.
And this descriptive thing he describes as simply drawing a line through a data cloud, something like this.
Right. Okay.
Yeah, but it's only very roughly fitting that's what I have in mind. So, but I like these prototypical disambiguation because with this I can better speak about it.
Sure. Yeah. Okay. Thanks. Yeah, I guess that's all the questions.
Do we have any more questions from the audience? And if not, let's wrap up our talk. So thank you very much, Dr. Georg Schollmeyer, again, for your time and just your wonderful presentation. Hopefully next time we'll be able to see you in person, either in an institute or maybe some of us will meet you in LMU at some point.
Yeah, thank you very much.
So if anyone would like to catch up on our this presentation, they can visit our website, riskinstitute.uk, or our talk will be available on YouTube as well. So thank you very much.
Thanks a lot.
Wishing everyone a lovely afternoon.
Thank you so much.
Thanks.
Thank you.